Hello guys! Today we are going to discuss the factors affecting the rate of reactions. Before we go to the factors, we first need to define reaction rate. Let us say for example, we have a reaction here. As you can see, it is separated by a single arrow, indicating that such reaction will come to completion, or if you will put it simply, it is irreversible. This arrow divides the reaction into two parts, the reactants on the left and the products on the right. The reaction rate is the speed that these reactants are converted into these products. So now that we have defined reaction rates, let us now go to the factors that may affect it. We have three, namely concentration, temperature, and the presence of a catalyst. Let us first look into concentration. Concentration is the amount of substance for a defined space. In this case, aqueous solutions will be used, which has concentrations expressed in moles per liter or simply molar, signified by a capital letter M. According to the collision theory, the increase in the concentration of a substance increases the collision of the reactants involved and will therefore promote an increase in reaction rate. Therefore, if you were to compare two same setups only differing in concentration, the reaction with a higher concentration shall proceed faster than that of a slower one. As for gases, concentration is varied by pressure, wherein higher pressure creates more concentration and less pressure creates less concentration of a gaseous substance. Think of this analogy. Imagine having a bunch of balls endlessly bouncing on a room. If we were to add more balls, more collision and contact could be made. Also, if the space of the room is decreased, even more collisions could occur, thus increasing reaction rate. Next, we also have temperature. Though some ionic compounds are exempted from this rule, temperature could also affect the rate of a substance. We could compare temperature to the amount of kinetic energy. As temperature increases, the kinetic energy increases as well. This indicates a more frequent and a more intense collision, which therefore indicates a higher rate of reaction. Finally, we have the presence of a catalyst. A catalyst is a substance that speeds up a reaction without affecting or altering the overall reaction. This catalyst provides alternative pathways that increase reaction rates by lowering activation energies. The activation energy, EA, is the kinetic energy that reactant molecules must have to reach the transition state. This transition state is defined as a relatively high energy state in which bonds in reactant molecules are partially broken and new ones are partially formed. When a catalyst is present, the energy barrier is lowered. Thus, more molecules possess the minimum kinetic energy necessary for reaction. There are two types of catalyst, homogeneous catalyst and heterogeneous catalyst. Homogeneous catalysts exist on the same phase as reactants. On the other hand, heterogeneous catalyst is present in a different phase from the reactants. Such catalysts are usually solids, and they lower activation energies by providing surfaces on which reactions can occur. Seems simple? Not quite. Now that you know these three factors, we will look into these factors in computations. For this, we will use two equations. For our first equation, we have this. Rate of reaction is equal to the rate of concentrations of the reactants raised to the responding coefficients. All this multiplied by a rate constant K. But what is K aside from isolating it in that equation? This is where our second equation, the Arrhenius equation, comes in. The Arrhenius equation aims to find the rate constant. It is computed by this equation. where A is the frequency factor, E is the activation energy, R is the gas constant equal to 0.0821 liters atmospheric pressure per mole Kelvin, and T is at temperature measured in Kelvin. If we were to look closely in the first equation, we could see that if we increase the concentration of a substance, it will yield a more positive value, obviously characterized by its presence as a numerator rather than a denominator in the equation. Going further, if we look into the Arrhenius equation, we have the other two factors discussed, the activation energy mentioned in the catalyst and the temperature. Since the whole exponent is negated, the activation energy should be low and the temperature should be high to make a less negative number. So that's it for this video. To know more about these equations and actual computations, don't forget to like and subscribe to our channel.